Welcome to the course on smart materials and intelligent system design. We have reached the intelligent system phase, right. It is the round 2 of the intelligent systems, and what we have studied in our last lecture, we have talked about these HBLS high bandwidth low strain smart actuators. We have also discussed that if you have to develop such actuators, how you have to employ intelligently multi-stayed piezoelectric material, and there are so many issues there. For example, the series and parallel modeling of mechanical systems, and similarly series and parallel modeling of electrical systems, and then the piezoelectric actuator modeling out of it. Then we also talked about the advantages, why we should do it, and how you can form such multi-layers. Now, in this talk we will go towards these intelligent systems, the other aspect of it, that is, as you know that for any piezoelectric material we have to electrode in order to see the deformation in the piezoelectric material. I told you already that every piezoelectric material basically works electrically like a capacitor. Now, for a capacitor like a parallel plate capacitor, if I exaggerate, then you need an electrode like this, then you have the piezoelectric material, if you consider this, and then you have the electrode. This is the conventional way of electroding. So, the top part is the electrode, right. What we will see in this discussion is that there are many ingenious way in which you can apply these, so this is the piezoelectric material in which you can actually apply this electrode. Okay. So, the design issues also related to this electrode configuration we will discuss about. Then we will see that when you will be using this, there will be little bit of heat generation in the system, and how that heat generation can influence your current generation. And also we will see some applications now, some intelligent MEMS devices which are based on smart materials. So, let us look into the electrode configurations first. The various electrode configurations are possible in such a system. One of the very popular one is called interdigital configuration. As you can see the interdigital configuration in this picture, if you slightly zoom it, then you would see that this is the way this electroding has been done. Okay. So, you can see these white parts where this electroding is happening to the system. So, this is an interdigitated in a kind of a spiral way that you are actually doing this electrode configuration. Now, the other one that we use for the multi-layer stacks is a plate through configuration, where you have direct electrodes between the two electrodes, you have direct connections here. Okay. So, like this is called a plate through configuration. Okay. Now, you can also have a configuration where you have these insulators and you have this plate through configuration. The other configuration that you will see in interdigital is that which will be having slit in it, like a slit in ceramic. Okay. So, you can see that there is a slit in it that essentially gives a good bondage between the system. You can also apply this slit thing in terms of the gaps in the electrodes, as you can see that there are gaps in the electrodes. Okay. So, like this, these gaps you can see. So, these are different ways in which you can actually configure the electrode, and each one of them has its own advantage in terms of how it would be deforming, how much of voltage you will be needing to make such a system. Now, once we make such complicated systems, of course, we have to see that mechanically it remains stable. One of the way in which, because it is so small, you will not be able to really judge it that whether you have done a correct interdigitation or not. One of the way to check that the perfect interdigitation is through acoustic emission. That means, you vibrate the whole system at a high frequency level and you check the acoustic emission from the system, and you will see that if the interdigital is done then there is one pattern that you would be able to see, and in the other case, if there are these floating electrodes, you would see that the acoustic performance is different. So, that is how you can actually check that what is the level of this interdigitation that has happened in the system. Now, even though interdigitated configuration is the most common and best suitable method for mass production also, and however, it actually creates non-uniform electric field, and that will create the edge stress concentration in the system. Imagine we are talking about ceramic materials where any form of stress concentration is very, very dangerous. It may lead to failure. That is one of the issues. In fact, all other configurations are developed to make the electric field more uniform and to reduce the stress concentration. That is why all these slitting and other techniques are used. Now, the limited strain that is developed at the edge of the interdigitated pattern can be actually expressed in terms of if you consider the D31 effective. So, instead of a simple D31, it will be a D31 effective, where this effective will have things like effective coupling constant S and T as a compliant modulus and compliance modulus and thickness of piezo, okay, and the subscript E denotes that of the electrode. So, you are taking the electrode also compliance and thickness into account in this model in order to calculate the effective D31 of the system. The other point that can happen is that what if there is delamination between the electrodes and the piezo layers. So, imagine that you have multiple like a stack you have, right. So, you have these electrodes in between. Okay. So, this is a through configuration, that plate through. So, if there is a delamination between the two, if the bonding does not happen properly, so then that is an issue, that actuator will not give us a proper performance. So, you have to control the organic binder, or you have to decrease the metal powder surface area. So, some of the things by which you can actually control the delamination in this kind of stacks. There are also effects of composition of the system, because the grain size of piezoelectric material that has a paramount importance in it. If you increase the grain size of this thing piezoelectric effect, it will increase. I told you that single crystal gives you maximum piezoelectric effect, but it will reduce the fracture toughness. Also, the effect of these grain size would affect the hysteresis and the dielectric loss. So, you have to think of what is the optimum grain size that you can go for, and the electrode variation also. For example, you can use a silver and palladium alloy, or you can use a copper nickel alloy system, and you would see that this type of systems are better as they have less thermal mismatch, because the temperature also would be an issue in terms of design of such a system. Now, how does the heat gets generated in the system, because you are applying the current and it is working like a capacitor. So, you can find out that what is the temperature that is developed in the system, where U is the dielectric loss per driving cycle and F is the driving frequency, V is the actuator volume, okay. That is the actuator volume that will come into the picture, and K is the conduction coefficient and A is the cross sectional area. So, the more the cross sectional area, the better it will be from the heat generation point of view. You will generate less heat, but in a mini actuator or a micro actuator, that conduction area is a problem. Now, how do we apply them in the form of a mechanism? Well, we have seen the amplified piezo actuators, and this is a micro version of that. So, you can see that there are some flexible hinges here, and this is what is called a Moonie amplification mechanism. Okay. So, these flexible hinges if you actuate at this point, for example, by using this piezo stacks here, as you can see at the center, and this flexible hinge will make this very predominant deflection of the system. So, this flexible hinges, you can see that in XY stages you can actually develop such flexible hinges in the system, and that is how the micro positioners are developed. We will show you the micro positioners. A very much similar, a little bit of a difference is there in Cymbal configuration, where instead of a hinge system, you have this kind of a system. Okay. So, you have this metal end caps there, which is shaped in a manner that it is similar to your amplified piezo actuator, though for amplified piezo actuator it was like a curved shape, but here it is having this type of a shape, and that is what is called a cymbal shape. So, you have a cymbal shape, you have Moonie shapes in order to mechanically amplify the voltage from the system, mechanically amplify the deflection of the system. Now, if you are generating heat, you have to be also cautious about the effect called pyroelectricity. So, we often say that there is a triangle. Okay. So, you have this electrical part in it, you have the mechanical part, and you have the thermal part. In fact, this triangle would many times can also become like a kind of a pyramidal shapes, etc. But in this case, if you consider that these three fields will constantly interact piezoelectric material, that means electricity can produce thermal effect and mechanical effect, we know. Thermal field can produce mechanical effect, we know. Mechanical effect will produce electricity in piezoelectric material. Mechanical effect can also generate heat and thermal effect in the system. And the most interesting thing is that the thermal effect can not only generate mechanical field, but also the electrical field. This last arrow is actually our pyroelectricity. So, the most common important example is gallium nitride semiconductor, where if you apply heat, you are going to see that there is a significant amount of positive and negative charge that is actually developing in the system. So, you can use it in terms of the pyroelectric material as a kind of a source of electric field. The other important thing is that instead of using these piezoelectric effect, sometimes people use an effect which is non-linear in nature, but it is called electrostriction. In this case, as you can see in the case of electrostriction, that this deflection is actually proportional to the square of the number of layers and also to the square of the voltage. So, which means that the deflection that you are getting from this system is enormously high, okay, for this kind of systems. So, it is n square instead of n. So, that is the point in which electrostrictors are better, but of course, not everything would be good. For example, you have to be cautious about the saturation, you have to be also cautious that this is essentially a nonlinear relationship. So, at what voltage you are getting what deflection in a nonlinear relationship is a little more tricky thing to handle. If I now compare the performance of such actuators, okay, so the first one is these MLA type of actuators, and here the driving voltage is about 100 volt, displacement is 10 micron meter, force is about 900 Newton. So, less displacement, but more force. You consider instead of the multi-layer actuator, if you consider the bimorph counterpart, driving voltage same, displacement you may get more, but force is very low. Rainbow, driving voltage little high, deflection increases, force is low. Cymbal, with the same driving voltage you get 40 millimeter, so you get a much higher deflection, force is also high. Moonie, same, you get a little lower deflection, and you can see that the force is, so you can see that the deflection is slightly lower, because of course, in comparison to multi-layer it is more, but the force is also not very high. So, from many points of view, you may say that Cymbal is a better configuration and its cost is also low. So, that is why Cymbal is very popular among these type of actuators. Now, I will also talk about some of the intelligent MEMS devices based on these actuators. Okay. What are these MEM systems we will talk about at a later stage. The most important one is what we call the Stewart platform. The Stewart platform is which is mostly used in space applications. It is based on a 6 degree of freedom system development. As you can see that there are 6 number of these actuators are there. And what is the effect of the application of these 6 actuators? You can see that there is this 6 degree of freedom implementation of the system. So, if you look at that, you can see that how beautifully you can actually control the motion of the top platform, as you can see here, with the use of these 6 actuating systems. So, that is a Stewart platform, and all these 6 actuators can be actually developed with the help of piezoelectric materials. So, that is a beautiful application of the smart material. Each one of the leg would consist of some linear piezoelectric actuator and a collocated force sensors and flexible tips for the connection to the base plates. And this structure is something that has its origin, original design is by Stewart of a 6 degree of freedom mechanism which simulated the flight conditions by generating general motions in space. So, it was initially used for flight simulating conditions. Typically, a Stewart platform will have a travel range of about 34 millimeter, loading capacity of about 5 kg force, actuator resolution is about 40 nanometer. So, high actuator resolution, and minimum incremental motion is about 0.2 micron meter, very precise positioning. And if you look at the repeatability, the precision is about 0.1 micron meter. So, all these things together make Stewart platform to be an excellent system which can be used either in vibration control, motion control, positionings, etc. Now, there is a micro positioning device also like this P545 Pi nano micro positioning device. If it is in a planar motion, then it is called XY micro positioning. If it is a kind of a special motion, then it is XYZ piezo stages. This one also has a sub nanometer resolution, very small resolution. So, that you can really use it in applications like micro fabrications, in applications like microscopes, confocal microscopes, etc. It has about 200 micron meter of travel range. So, not a very high range, but it has sub nanometer of resolution, extremely fast step and settle from 5 millisecond you get this entire thing. So, you can record very fast kind of motions of systems through this device. There is another interesting device which is known as the energy harvesting system. This can be used in various purposes. For example, a typical thermoelectric energy harvesting system. So, what it will have is it will have a thermoelectric generator, it will have a heat sink, voltage regulation, charge management and energy storage. Typically, we use such a system inside aircraft engine, for example, as you can see that this is a GE engine where this has been used. So, if you want to really check the health of the engine from inside, you need to have some kind of a power generation for the sensors. Now, how do you get power for the sensors? Well, I have talked about pyroelectricity in gallium arsenide. So, using very similar type of things, if you can extract the heat that it is subjected to, this part is very hot, then that heat can be used to generate electricity, and then that electricity can be used. So, these are the thermoelectric generators, can be used to actually give power to the wireless transmitters, through the wireless transmitters to all the wireless sensor networks. So, we call it WSN, which essentially means wireless sensor network, where you can use this kind of energy harvesting devices. There are other applications also of energy harvesting device, which I will discuss subsequently. Now, in many such cases, you actually develop from the linear motion to a rotary motion in a piezoelectric actuator. So, you can see a typical such system, as you can see here, that it is typically used in motor kind of things. So, you are giving axial motion, but you look at that blue line, how by giving this eccentric actuation you can actually generate a rotational motion in the system. So, that is about this kind of energy harvesting sensors. The another very interesting application is in terms of active shape control, and that is used by developing laser micro machined and magnetically functionalized hygroscopic bilayers. So, it is something like sellotape kind of a thing, but you need to laser micro machine it to develop this kind of a system, as you can see, and it is a very flexible actuator. Basically, it is a electroactive polymer in nature. So, it is EAP, I have talked about it earlier, and using a small voltage you can see here that how it is actually getting deformed, almost like to form something like a finger ends, and you can actually extract pollutions through this. So, that is there is also another type of an application of this type of systems through active shape control. This is what we will come to an end in this lecture. In the next lecture, we will talk about a case history of sensor application. We will talk about MEMS based accelerometers and how to develop the MEMS or the micro electromechanical system. Thank you.